We're going to talk about substitution. Substitution is undoing the chain rule. And actually, if you did the chain rule using the U and the V notation and the U and DU notation that they did in Chapter 12, it actually kind of follows a little more easily when we do this. So if we're looking at the integral of 2x cubed plus 1 raised to the 4th power times 6x squared, what you need to notice here is that there's two functions going on, and one of them actually looks like a chain rule function. And that's going to be the thing that will help you know when you're going to have to do this, what's called substitution. Okay? The part of it that looks like chain rule is the 2x cubed plus 1 to the 4th power. So the question you ask yourself when you see something like that that looks like chain rule is, okay, what is the derivative that's on the inside of that function? Because if this is the derivative of the original function, then I have to have the derivative of what's inside those parentheses as part of it. Okay? If the original problem was a chain rule, then we have to have the derivative of the inside part of the function as part of the final derivative. So what is the derivative of 2x cubed plus 1? 6x squared. So then the question you have to ask yourself is 6x squared part of the derivative that I'm trying to anti-differentiate? And in this case, it is. Okay? So the way that we actually do that is we're going to do what's called a U substitution. The chain rule part is going to be the U. And we have to have DU to be able to finish the process. But once we have it, we don't pay any more attention to it. That's the part that kind of puzzles some people, like, well, I had to go to a lot of trouble to get that. And now you're telling me I just throw it away? But that is what happens. So the way that we actually do this is we're going to have that U is equal to this 2x cubed plus 1, so it's actually the integral of U to the 4th power. And then du is actually 6x squared dx. So this is what we actually have from that. This is the part that's U. You still have the parentheses in the 4th power, just like you did with chain rule. But this is the derivative of what's inside the parentheses, and you've got to have that before you can finish. But once you've got that, this becomes a power rule problem. So with that substitution, the antiderivative of u to the 4th is going to be u to the 5th divided by 5. And then, of course, there's always going to be that constant. But once you realize that all you're doing is taking what's in those parentheses and you're using the power rule on it, then you're going to add 1 to the power and divide by that same power and add a constant. So this is going to be the original chain rule part of it, but you're going to increase the power by 1 and then divide by that power. Okay? So this is actually the derivative of the family of functions, or this is actually the family of functions that has that as its derivative. If we knew what the constant was, we would know the specific function. So we're going to do some examples. But remember that you can always take what you have left because you know chain rule. You take what you wind up with and you apply chain rule and take its derivative, you should come back to what you started with. Okay? Always remember that. So here's our first example. What part of it do you think is the chain rule? That's right, that's the 3x squared plus 4 in parentheses to the 7th power. So I'm going to switch over and use the overhead. And we're going to see if we can work that problem. So what you've just told me is that you think this is what they're calling u. Okay? So what we're doing, we think, is the integral of u to the 7th power. But then we have a question. Is 6x dx the derivative of u? Is du, or u prime, if you want to think of it that way, is du equal to 6x dx? What's the derivative of 3x squared plus 4? It's 6x, and of course dx just says it's derivative. Okay? So yes, we have du. So then the way that we would do this integration is we would say that this is u, 7 plus 1 is to the 8th power, divided by 8, plus some constant. And then all we're going to do is replace u with what it was to start with. So there's your family of functions that was the derivative of. And if we were to actually take the derivative of that function, we should get this back. We should be able to check it. So if I take the derivative of this over 8, I could also look at it, that's 1 over 8 times 3x squared plus 4 to the 8th power. And of course the derivative of the constant is going to be 0, so I can forget about it. Then this is going to be 3x squared plus 4 to the 7th power. 1 over 8 still in the front. And then this is going to be 2 times 3 is 6x squared so something disappeared. It should be 6x. Yeah. But something still, we have to figure out where that went. Oh, yeah, because we would multiply it by 8. Sorry. Yeah, I didn't drop it down in front. I forgot to drop my 8 down in front. When I'm doing the derivative, it comes down here. Somehow my brain just locked up. So, yeah, that does disappear. And we do get back what we started with. It's far too late. I have a lot of respect for you guys. Because I know you've worked all day, too, and you're still here and trying to learn this. Okay, we'll try another one. Here we've got this, and the only rule we've got to work with is power rule. So the first thing we're going to do is we're going to rewrite that as a power. And then what's left is x dx. So then our question becomes, okay, what's the derivative? I'm sorry, x squared. I left out my square. And that would have been important. So what's the derivative of x cubed? If this is going to be u. Okay, du is 3x squared. So then the question is, do I have du in the problem? What am I missing? I'm missing the 3. I got the x squared, no problem. I need a 3. And the 3 wasn't there to start with. I can't just throw it in. But what I can do is if I multiply inside by 3, I can multiply on the outside by 1 over 3 because 1/3 times 3 is 1, and now I've changed nothing. I didn't just throw in the 3. I threw it in, then I took it back out by multiplying by 1/3. And that kind of goes back to what happened with that 1/8 in that other problem. When that power came down in front and 8 times 1/8, that became 1 and it disappeared. So that 3 times 1/3 is going to disappear into the mix. It's not going to change anything. Now that I've done that, I just simply do the same thing I did before. This is actually going to be u to the 1/2 power with a 1/3 in front of it. And this is all just going to be du. So with the substitution, this is going to be 1/3 times u to the 1/2 plus 1 divided by 1/2 plus 1, and then plus some constant out here. And since 1/2 plus 1 is equal to 3/2, then what's going to happen is I've got this. I need to figure out where to put that, so I think I'm just going to come over here because I didn't leave myself enough room. So the 2 is going to come up here with the u. And the 3 is going to stay where it is. 1 times 2u to the 3/2 power is going to be 2u to the 3/2 power, and then 3 times 3 is going to be 9, plus a constant. And even though you think, the u is actually an annoyance and aggravating, but it's easier to write it and eliminate the clutter that you've got with this until you go to your last step. So then at this point, I know this is actually the complete antiderivative, and I can just plug back in what u was. So plugging back in for u, what u was to begin with, there's your final answer. Look at it and make sure you follow everything. But how did it get to be? Okay, let me redo that step. It's, yeah, I think I heard you right. It is technically 1/3 times u to the 3/2, and if you're dividing by 3/2, that's the same as multiplying by 2 over 3. Is that what you said? you could do that. Except you have a 2 out in the front, so you would have said it was 2/3. And then that would have been divided by 3. And actually, that's equivalent to what I said. It's actually the same thing. And if you were to type that in My Math Lab, it should take that as an answer. You just have to be very careful that you use your fractions. Now, if you were typing it into the calculator, that would be a pain in the hind end to have to type in because of all the parentheses you'd have to do. Unless you have, now if you've got the 84, it makes fractions, but the 83 doesn't make fractions. You have to put all the fractions in parentheses. Yeah, these two are equivalent to each other. That's fine. Okay, does anybody else have any questions? Okay, now this one looks a little tricky, but doesn't have to be if we rewrite it. First thing you want to do on this one is rewrite it to where the power is negative, and then it'll make more sense. And then what you have left is x plus 3 dx. And since u is usually the thing that's got the power around it, then we're thinking probably this is u. So then the question becomes, what is du? And du is 2x plus 6. Well, I don't have 2x plus 6. All I've got is x plus 3. But if I multiplied it by 2, that would be 2x plus 6. But since I can't just toss in some random 2, what else do I need to toss in? A half. So I put it out front. So now that I've done that, I'm going to take the integral of what I'm calling u to the negative 2 power, and all of this is du, which means it's just going to disappear and get out of the way. So that's going to be 1/2. U to the negative 2 is going to be u to the negative 2 plus 1, which will be just u. That's going to be divided by 1. So 1 times u is going to be u, and 2 times 1 is going to be 2. It's going to be u over 2, or 1. You could keep it as 1/2 u if you wanted to, but u over 2 might be easier to deal with. And of course, we have to add the constant to it. But then at the end, we're going to go back and we're going to swap that back in for u. So there's your parent function. Okay, that's fine. If you don't understand, I'd rather answer you now. Good point. You are correct. Somehow I managed to take negative 2 and add 1 to it and turned into positive 1. See, I'm glad you asked the question. Don't ever stop asking questions. There might be a reason. You needed that negative one part. It didn't change anything else. No, it doesn't change anything else. It might change the way that you would want to write it if you like juggling things around algebraically, but, you know, we like to keep it simple, so it's not going to change anything else we need to do. Okay?
If you simplify that, would it still show on that like you said, was 1 over 2x squared?
Yes, it would still work. If you actually wanted to write it this way, that would be fine. And my math lab would also recognize it if you wrote it this way. That would also be fine. All of those are the same. And I have folks in both my classes that they'll go ahead and simplify it because they don't like the way it looks to start with, and that's fine with me. You can simplify it. But I'm still going to look at the first step to make sure you did the first step right. Because as long as you got that, I'm not going to count off if you mess up a little bit after that. Okay? So do you think U substitution is going to be something you can handle? Most of y'all did pretty well. With practice, yeah. Most of y'all did pretty well on the U substitution on the Chapter 12, though. So I think you'll be okay. Now let's try one more just to be sure we've got it. I'm going to let y'all work it first this time, and then I'll come in and work it. So I'll give you a couple minutes to work it and see. Let's see if you got this. What do you think U is? Okay. I'm actually going to leave it this way. Now the question here is 2x minus 3 dx, is that du? Yes. Okay, so we got a big check on that. That means we're doing the integral of 1 over u. We're not using the power rule. So that means when we do this, that becomes 1 over, becomes ln of u plus a constant. And since u is this, then that's going to be the natural logarithm of x squared minus 3x plus a constant. And there's your family of functions. Did y'all get that? That's right. High fives. Y'all deserve it. Y'all done good. You did good. Okay. You sort of do, and if you do, you just put them instead of the parentheses, and it wouldn't be wrong. But in this case, as it mentioned in that one earlier about x squared plus 1 would never be negative, well, actually, x squared minus 3x, I don't care what x is, it's never going to be negative, because squaring makes things grow a lot faster than multiplying by 3, so it's always going to be a big number minus a little number, which will always be positive. And that's why I did the think and didn't put them in there. But you do need, but that is a good point. You do need to watch for that. Yeah. So, yeah, you probably should do that. It should actually always be the absolute value. It's safer to put it in there just in case the function ever were to possibly ever be negative. Okay, but since the real thing is usually if you have a u, it's because it's some little function, and usually it has a power or something with it anyway, or a square root function. So it's really kind of odd that you ever have a u that could ever be negative. But on the off chance that you would, yeah, you really need to pay attention to that, especially if you're going to plug a number into it. Okay, I want to say the word last example because I'm going to change something. Our last example, we have e raised to the power of x cubed. And that's multiplied by x squared, and then there's a dx. Now, if you're looking at that, which one of those two things is more complicated? You know, the e raised to that power, because it's a function on the power. So that's probably going to be where it is. This is probably e to the u, and that function is the u, that x cubed. So if u is the x cubed, then what is du? Two x bring the 3 down in front, and it'd be 3x squared. Okay? Do we have 3x squared? No. Could we have 3x squared? Yes. We could have it by simply putting in 3 over here and 1/3 on the outside. So that means that this is e to the u and this is du. And then the 1/3 times the integral of e to the u du is simply 1/3 times e to the u. Nothing changes. So it's just like e to the x, e to the u is its own derivative. We've already figured the derivative of its power. So then all we do is then go back and change u out for what it was to start with. And what it was to start with was x to the 3rd. And then add the constant to it. And if you wanted to write that as e to the x to the e raised to the power x to the 3rd divided by 3, that would be okay also. You can do that or keep the fraction, either one. Okay? I think I must have left this thing way while back. Okay. So this is basically what you're going to have on a formula sheet for the next exam. You're going to have all of those plus the formulas from 15.1 that I showed you. I don't know how helpful formulas are, though, when it comes to actually doing these things. There is another example on this section, but I went and looked through the other stuff while y'all were working on that one, and we're not going to do that example. I took out the one, I put a note in and said don't do the last homework problem for 5.2 because I know that's not on the test. And the reason we're not going to do it is because it takes another little algebra technique that I think winds up getting people confused, and since it doesn't show up in anything we need to do after that, we'll just not do that one. So we'll leave that one out. So, let's see. I don't think we've got any more examples except that one. We have one demand function, so we will do the demand function. So the one that I'm skipping is this one. You want to just draw an X over that one, you can skip that one. And the matching problem in your homework assignment for Shelby is the very last problem on Shelby. So, just cross it off. You don't have to do that one. You can leave it off. I will not count it. But we will do the demand problem because applications are, once again, something we're going to have to know how to do. But before we do the demand problem, here's a little, this is in your notes and you may find it helpful. When you're doing substitution, it's kind of like the same thing that I told you when we were doing chain rule. In general, there's three cases. When you're doing substitution, you're either going to have the quantity under a root or raised to a power. It might be a quantity in the denominator. Always look at the denominator first, because it's more likely to be in the denominator than it is to be in the numerator. And the third one is always look at the exponent on e. And if it's e raised to some power that's a function, that's u. Okay? So those are the cases. And then the thing about the integrands needing to be rearranged, that was that last problem, and that's why we're not doing it. We don't want to have to fool with rearranging integrands. So we're going to go to the demand function that we have. It says the research department for a hardware chain determined that at one store the marginal price of X boxes per week of a particular type of nails has this function, and that is the derivative, not the function. Since that is P prime, then the function was the function for price, which means that it's the demand, and it asks us to find the demand equation. And price is part of the demand equation. The other part of the demand equation is the quantity. Okay? So the first thing we need to do is we need to integrate that function. So that's what we're going to do. Looking at that function, the first thing that I notice is we've got something that appears that it might be a u substitution. It's in the denominator and it's raised to a power. So I'm thinking this might be 2x plus 15 would be u. So that means that might be u to the third power. So my question would be then, well, okay, then what would du be if that was the case? Now, du would be 2. Well, the thing is, I don't have 2. I got negative 4,000 up there. But that has a factor of 2 in it, right? What we need to do first, we're going to say let u equal the 2x plus 15. And that means that du is equal to 2. And then this integral that we're looking for becomes negative 4,000 and I'm going to pull the dx up there with that. There's what I'm hoping to turn into du, and then the rest of it is u to the third power. So somehow I've got to turn this into that. Actually, that really is 2 dx, but That's kind of redundant. So the way that I need to do that is, first of all, I'm going to, oh, and this is actually to the negative 3. Sorry about that. That's actually to the negative 3. But that's still u. I can rethink what this is. du is 2. I'm going to ignore the fact that I have that, because what I'm going to do with that is I'm going to pull it out front. And du is 2du. But if I pin that 2 there, because actually
I didn't have it here, if I throw in that 2 there, I have to throw in 1/2 out front. Okay? So that means what actually is going to be in the front of this function, since that's du and it's going to disappear, is going to be 1/2 times negative 4,000, which is going to be negative 2,000. And then u to the negative 3 is going to be 2x plus 15. And negative 3 add 1 is negative 2 plus a constant. So is everybody with me so far? Okay. It is over negative 2. It is over negative 2. I think you're going to do great on the next test, because you're catching it now. Okay? So here at the bottom, we're going to try to simplify this now. Negative 2 cancels into negative 2,000 and becomes 1,000. So our function is going to be f of x is equal to, and I'm going to actually put this back in the denominator, 1,000 over 2x plus 15, and now it's going to be squared plus a constant. And there's a reason that I actually did that, because it'll make the arithmetic we've got to do in a minute a little bit easier. So there's our indefinite integral, basically is what that is, okay? Then we've got some more information up here. We've got some information about money. The demand for this type of nails is 10 boxes. X is actually the number of boxes. And f of x is actually a price function, because this was the derivative of price. And it says the price of the box of nails is $4. So what they've given us at that point is they've given us the information to figure out what that constant actually is. So if we go, and actually I'm going to pull it off onto another piece of paper so we don't have to be crowded to do this. So if we solve the equation, 4 is equal to 1,000 over 2 times 10 plus 15, quantity squared, plus C, then we have 4 minus 1,000 over 2 times 10 is 20 plus 15, and that squared is equal to the constant. And at this point, most of us would probably hit our calculators because I don't want to square 35 in my head. But if I did the math right earlier, then 1,000 over 35 squared is about 82 cents. Okay? So that means your constant is actually 4 minus 82 would be $3.18. So that means then that your price function is equal to 1,000 over 2x plus 15, quantity squared, plus $3.18. Okay? And that is the demand function in terms of quantity. Remember before we had the demand in terms of price. Now the demand actually is representing quantity. It's a function of quantity. Okay, do I need to back up? Okay. And since that demand is in terms of quantity, then the actual demand is a dollars amount.
So I'm getting a little confused on just kind of looking at the problem for kind of information I need. 10 boxes is quantity, and I'm
Right.
quantity and price, but just looking at it from the equation, he has equal to like everything. Basically, you have 2 x's there, but the 2 x's have 2 different values. So would like because you said it's
Okay.
solved, is there another way?
That's actually P of 10, and P of 10 is equal to $4. Does that make more sense? I didn't really make that plain, I don't think. Because I was saying when x is equal to 10 down there, then the value of the function for 10 was $4. So the $4 is actually P of 10. It was given to us. That we don't need to worry about it. It has to be given to you. And since the price function, the price is $4 and the quantity is $10, so when you have $10 or 10 boxes, when you have 10 boxes, then the price is going to be $4 per box. Okay? Now, I'm sorry I didn't make that real clear.